Hello and welcome. We have spent a lot of time talking about how to take the derivative. We've talked about the product rule, the quotient rule, the chain rule, the derivative of different trig functions, all kinds of different things involving derivatives. And what we're going to start doing now is we're going to start looking at the inverse operation of a derivative, or the opposite of a derivative, which is called an antiderivative. So in this section, we're going to start focusing on what is an antiderivative, or what is the opposite of a derivative. We're going to use some of the skills and foundation that we built when taking derivatives to sort of work backwards to discovering original functions. And then we're going to formalize the notation used for indefinite integration. And then in the next video, we're going to formalize more of those rules and work through some more examples. So before we jump into an antiderivative, what I want you to do is to think, looking at these three problems in the warm-up up here, I want you to think about, if you were given this derivative, what function is that the derivative of? So thinking backwards, asking yourself, how do I undo what was done when taking the derivative to get back to the original function? So go ahead and pause the video and look at numbers 1 and 2 and 3 and see if you can come up with a function whose derivative is the derivative that you're given for each of these problems. So the first thing that we do if we look at something polynomial-like is that when we're taking the derivative, we drop this number down, that was our exponent, and we decrease that exponent by 1. So if we look, and we're trying to think backwards here, if this exponent is 4 after we decreased it by 1, then its original exponent before we did that, before we took the derivative, should be 5. And that does make sense. If I have x to the 5th and I take the derivative, I would bring the 5 down and I would have x to the 4th left over. Using that same logic, this term here has an x to the 1st power. If I increase that exponent by 1, I get x to the 2nd, and that makes sense. If I take the derivative of x squared, I get back to 2x. So this function in red here, if I take the derivative, I get this derivative that was given in warm-up number 1. So go ahead and pause the video if you didn't already get a chance to work on number 2. So what I'm asking myself on number 2 is, what do I take the derivative of to get cosine? Well, the derivative of sine is cosine. And then I'm asking myself, what do I take the derivative of to get 1? Well, I would get 1 if I had x. The derivative of x is 1. So again, I could take the derivative of this blue f of x function here, and that would get me back to the original function f prime of x. Number 3 is challenging, and I'm going to give you a hint if you haven't tried this already. This looks like the result of a product rule since I have this plus sign here. So knowing that, see if you can try and work backwards to get there. Okay, so what I know when I have a product rule is that the first term in each part is function 1, and the second term in each part is function 2. And again, I just assumed that maybe there was a product rule going on because these two functions seemed really similar. So what I'm really saying is the derivative of the first function times the second function, well, 2x is the derivative of x squared, right? That's why we have x squared right here. Times the second function, which was just sine of x. So sine of x is here, and then the derivative of sine of x is here. That's how our product rule works. Derivative of the first function, 2x, keep the second function the same, sine of x, plus keep the first function the same, x squared, take the derivative of the second function, cosine x. So if I started with this function, we could work and take the derivative using the product rule to get us to this derivative for number 3. That one was a little bit tricky. So most of what we have been doing is thinking in our heads and working backwards from what we know about derivatives to get to a function. And that's called finding the antiderivative. So the antiderivative is basically reversing the derivative. It's finding the original function. Another name for that, so besides finding the antiderivative, you may also hear, and we'll hear very often in this class, this referred to as integrating a function. And we're going to learn some notation that goes with that later in this video. So before we get to that formal notation, I want you to think about these three functions down here, number 1, number 2, and number 3. And go ahead and pause the video and take the derivative of each of those 3 functions. So hopefully you notice that each of these 3 functions, all of which are different, none of them are the exact same function, each of them do actually have the same exact derivative. So that's what I noticed. I'm hoping that's what you noticed as well. So something to notice is that all 3 of these functions aren't completely different. They all have the same first term, 3x squared, 3x squared, 3x squared. So they are similar functions. They're all quadratics with an a value of 3. Their difference is a constant. So they all differ by a constant. Because of that, if we start with the derivative, so if we started and I said the derivative of a function, is 6x, and I asked you what is the original function, you could argue that there's an infinite number of possibilities. All 3 of these examples could be the original function. So how do we distinguish between? How do we start with the derivative and find the original function, but account for the fact that there's an infinite number of right answers because there's an infinite number of constants? So here we just saw 3 examples. And how we do that is by using something to hold the place of what that constant is. So when we're finding an antiderivative, because we can't be sure about a constant, we include a plus c afterwards to show that there could be a constant added to that function. So looking back at this example we were just talking about, what is f of x, we could say that f of x is 3x squared plus some c value, and that c value is saying it could be any of these functions or an infinite number of other options as well. So plus c holds the place of some arbitrary constant, and we call that plus c the constant of integration. So let's look at some practice problems. Given a derivative, use what we know about derivatives to try and work backwards to find the antiderivative f of x plus c. So again, when I'm thinking about 3x squared, I'm thinking that originally that exponent would be 1 more, which would be x to the 3rd. And I know I need to hold some placeholder for c. And then off to the side or in my head, I want to confirm that this does actually make sense. If I took the derivative here, I would get 3x squared, and the derivative of c, whatever number that is, would be 0. So I have confirmed for myself that this function does represent every possible antiderivative of the derivative 3x squared. So go ahead and pause the video and try and work through numbers 2 and 3 on your own, and then unpause the video and see how you did. All right, hopefully you have had some time to look at these. So on number 2, I'm asking myself, what do I take the derivative of to get negative sign? Well, the derivative of cosine is negative sign, so that covers this piece here. Then I want to know what do I take the derivative of to get 1? Well, the derivative of x is going to be 1. And then for each of these antiderivatives, I need a plus c to hold the placeholder for any constant. And again, we could check this. We could check that this works by taking the derivative. The derivative of cosine of x is negative sine of x. The derivative of x is 1. The derivative of the constant is 0. So we have gotten back to our derivative. Okay, number 3. So I know that if I have x squared, to get back, I need to increase that exponent by 1. Now, what I notice is that if I took the derivative of this piece I just came up with here, I would get 3x squared. But I'm not supposed to get a 3x squared. What coefficient is in front of x squared here? Well, that coefficient is 1. So 1x squared. And how do I get that? Well, I need something to make this 3 go away. So I could divide by 3. So I'm going to put this over 3 so that when this 3 drops down, it divides out with the 3 in the denominator. Similarly, my second term is just x. If I increase the exponent there by 1, I would get x squared. But if I took the derivative of that, I would get 2x. And I don't want 2x, I want just x. So I need to divide 2 to get rid of that 2 in front. And just like on the example before, to take the derivative of something and get 1, I need to take the derivative of x and each problem here needs to have a plus c value. And you could now take the derivative to confirm that we do in fact end up with the derivative that we had here. So the last thing that I want to do in this video is show you what an integration, or what the symbol used for an integration is, and do a few practice problems using that notation. What we'll do in the next video is formalize some of the things that we've actually been doing in our head, the ways we've been working backwards, work through some more examples, and talk about what happens if we don't want to have a plus c. So let's finish up by looking at the notation for an indefinite integral. So instead of saying find the antiderivative, what you will typically see is a symbol that basically means that, and that symbol is called an integral, and that symbol is right here. To me, it kind of looks like something you would see in a music book, and I say that having really no background in music whatsoever. I have heard it referred to as the fancy F before, but this is the symbol for an integral. Since what we're doing when we're integrating is finding the antiderivative, we see the integral of the derivative, and then we see this thing, this dx here. And this dx is telling us what we are integrating with respect to. So it means we're integrating with respect to x in this case. If our entire problem was in terms of another variable, then we would have another variable there. So the dx tells us with what variable we're integrating. And that shouldn't seem so weird. We've talked about having dx when we were taking derivatives earlier in the year. This was a notation that we had used for that. So now we're integrating with respect to x instead of taking the derivative with respect to x. So derivative with respect to x, integral with respect to x. So if I was to read this statement out loud, I would say the integral of f prime of x dx is f of x plus c. Again, where this c is our constant of integration. So this notation may look a little foreign or seem a little weird to begin with, but it does make it easier to see what's being asked. And that becomes clear when we look at our last three examples for this video, 4, 5, and 6. So it says, use what you know about derivatives to find the indefinite integral of each function. Call the antiderivative f of x. So we're going to say that when we integrate this, we end up with f of x. So again, what we're doing is we're saying, what is secant squared x the derivative of? Because what we're trying to do is find the antiderivative. So the integral of secant squared x dx is the same thing as whatever function I took the derivative of to get secant squared. Well, we know that the derivative of tangent of x is secant squared of x, and we now know that we need to add a constant of integration to each problem. Number 5, I'm actually going to start by rewriting this with rational exponents. This is 4/3 times x to the power of 1/3 dx. And now remember, the exponent would be increased by 1 before we took the derivative. So if I add 1 to 1/3 that was already there, I would get 4/3, which makes sense. That's the scalar, that's the number that's being multiplied in front here. So if I just rewrote this as x to the 4/3 power, and I took the derivative, it would become 4/3 x to the 1/3 power, which is what we need. And then we need to make sure we don't forget our plus c. This last one is super tricky, but I wanted to end with a challenging one like the warm-up problem for number 3. So what I notice here is that it seems like there's a relationship between 3x squared and x to the third. One of them is the derivative of the other. Similarly, there seems to be a relationship between cosine of x and sine of x. One of them is the derivative of the other. So if you think you can get here, go ahead and pause the video and see if you can do that. So what I notice here is that this, again, looks like the product rule has occurred. And my ultimate goal would be to undo the product rule so that I can find the antiderivative. So if this is my derivative, that makes x to the third my original function. And if this was the derivative, then cosine must be my original function. And if I took the derivative of this, 3x squared, keep the second function the same, plus keep the first function the same and multiply by the derivative, which is negative sign. And that does get me up into this piece right here, which is known as the integrand. So the part inside the integral is called the integrand. Inside the integral is called the integrand. And then to close this off, I need to make sure I have a plus c there. So let's recap what we covered in this video and talk about what we're covering again in the next video. So in this video, we defined what an antiderivative is. An antiderivative is the function that we take the derivative of to get a derivative that's given. The process of finding that function is called finding the antiderivative or integrating a function. We then looked at examples where we had to use tricks that we learned from derivatives to work backwards. And we talked about how because the derivative of a constant is 0, if we're working backwards to find the original function, we always need to have a plus c value there to hold the place of any potential constant that could have been there to begin with. Then we wrapped up by looking at this notation, the integral symbol, the integral of a derivative with respect to x gives us the original function plus that arbitrary constant, and we worked through some examples where we had that new fancier notation. In the next video, we're going to formalize some of the rules that we have been using without sort of stating them here, work through some more examples, and then we're going to talk about how you could actually find the exact value of c if you're given an initial condition. So write down any questions you have, and I look forward to supporting you on this. Thanks for listening.